This is the second part of the fourth lecture in quantitative big imaging, and this is a pre-recording for the classroom lecture. And now we're going to talk about segmentation and where does it get us. So we can, of course, compute a decimal value or something even more complicated from the images, and we want to convert it into something less complicated. So for example, in images, color images, you have three values in RGB. You can have a spectrum from hyperspectral imaging, or you could also having a vector or tensor describing mechanical stress. And that we want to reduce as much as possible, usually into just true and false, if it is something or not. But in some cases you can have multiple phases, so it could be that some phase correspond to bone, some to air, and another one cellular tissue. And here, if you remember, we had the tomography data, 32 bits, a really big chunk, 56 gigabytes per sample. And if we reduce this to 1 bit per sample instead of 32, we have reduced the whole data from 56 gigabytes into 1.75 gigabytes per sample. And all of a sudden, the data starts to be possible to handle. And now we just create little example images. In this case, it's more or less a cross that is added noise. A little bit complicated equation here, but in principle, we create an X and Y field. And from that, we do something with the cosine, and then on top of it, we add a random uniform noise. And that gives us this image, which we're going to analyze. Oops. And first we can do is to take a look at the histogram, which is the probability density function of this particular image. And we can see that there is a big chunk of pixels having values less than 0.4. And then we have some fewer pixels that are above this value. And this is already an indication. If you look here at this image, you have the background, which are clearly many more pixels than the cross itself. So let's take a look at what we can do. First, we want to identify where is the cross, and that can be done by applying a threshold to the image. And the threshold application is that you go pixel by pixel and check, is the pixel value greater than 0.4 or is it less than 0.4? And then you set a 1 or a 0 to it. In Python, this looks like following. We have the threshold value. It's actually ambitious to write a separate variable for it, but for the sake of readability, it makes sense to actually describe what it is. Then our threshold image is the cross image is greater than the threshold. And when you execute this, you have got your binarized image. And looking at it, the threshold value at 0.4 would be here. And looks quite reasonable to have it here. And if you look at the resulting segmentation, the green boxes here, they correspond to the segmented values that should belong to the cross. And it's not too bad. We have some that go outside, but mostly it's doing the right thing. Maybe we should test with another threshold like 0.45 or something, and then we will get a better result. But for now, I think we should be happy with this 0.4. And what is the effect of choosing different thresholds in this image? So here I have a long list of different threshold values, and let's see what happens. So if we set it to 0.1, it's clearly too low. And if we go back to the previous slide, you can see 0.1 was here, and we have a lot of background which would be segmented as foreground. So this we don't want. And same is for 0.26. You still have a number of wrong classifications, but it's better. And then we come to the 0.42. It's about the same as 0.4. We will take it one step further to go to 0.58. Oh, wow. Now we got a nice cross and it looks like we are clean. Now, if we would continue, then we would all of a sudden start losing more and more pixels from the cross too. So that is also not a good idea. And if you go really extreme up to 0.9, you see that most of the cross is not even detected. So looking at the real image, now we want to segment cells. And if you look at the cell microscope image, then we say that cells absorb light and therefore you have darker regions where the cells are and lighter regions where there are no cells. So looking at this image, you can see we have a lot of dark spots, which would be the cells, and a lot of background too, which would be just the substrate we are on. And looking at the histogram here, we have a very large peak at high values. That would be the background. And then we have a long tail here that corresponds to the cells and other things. So it's not really sure what we have. And now let's see what happens if we start putting different threshold values on this image. So here I set the threshold value to 100. Just going back again. You can see here is the 100 and you have only this piece of the tail. And yeah, we detect some, not all, but at least some. And it also looks like we don't catch everything of the cell. So there may be a brighter halo around them. So this is not really a good threshold. Then we go on and increase our threshold to different values. And you see that's around 140 or 160. It starts looking quite good, but we still have some cases where you miss the cells and you can even see that there is a trend going diagonally from the upper left corner to the lower right corner. And this becomes more and more dominant when we increase the threshold even more. You can see here you have a clear over-segmentation all of a sudden. So we are actually segmenting pixels that are not cells anymore. The reason for this is that we have an inhomogeneous illumination of this image. So it is darker down here than it's up here. So in this case, the image wasn't really well normalized, and therefore we also have a trend, a spatial trend in how the segmentation performs. Now we can also look at other kinds of images. We can take a look at, for example, a vector image. Now we produce some code to do a mesh grid. So that's again 2 matrices, one where the x values increase for every row, and the other one which the values increase in the vertical direction for the y values. Then we create some kind of intensity image with a cosine and some noise in it. And one way of presenting it is to create a data frame where we have x, y, and detector value. And also what we're going to do is we are going to create a vector valued image. So here we add 2 vectors which depend on some calculation here of the positions. And finally, you can see here our table. If we look at the sample of this data frame, sample takes a random selection of values from the table just to give you a little overview of what the values look like. Last week we looked at the command head, or it's actually also exists the tail, and those show the first 5 rows from the data frame. But this one selects 5 randomly somewhere in the data set. Now we can look at this data with something called a pair plot, which you find in the package called Seaborn. And pair plot plots all the columns against each other as bivariate histograms. And x against y and y against x just gives you a uniform distribution of everything. Doesn't tell very much, so we could actually skip those. Then we have the eye detector, which you can see that it has the intensity, has values in the lower end, and it's relatively uniformly distributed in the x direction and also in the y direction. Now if we start looking at x against the x component of the vector, you see some trend, and also if you look at the y component of the vector, you also see some trend, but it's not really clear yet. But when you come down to the vector against vector, then you see that actually the vector information plots a circle. So this pair plot can be very useful if you have many variables and you want to compare them to each other. So it's the different types of histograms displaying all the columns in the data. Looking at the vector field, it looks like this. And here we use the so-called quiver function, which is a part of matplotlib. And the parameters here, you show, first you give the coordinates, then you give the x vector length, the y vector length, and then you give a color, and you tell which color map. And with that, we have arrows with the array pointing outwards from the center. And we can also look at it in different ways. We can try to now apply a threshold. So let's try to see what happens if we segment all the components where the x and y component of the vector is greater than a quarter. Then we set it to equal to 1, and otherwise we set it to 0. And do some nice coloring of it, and then you see this is the section that we have segmented using this thresholding approach. And we can also look at the histograms of the vector and see what happens. So here we have the x component of the vector and the y component of the vector, and this would be the thresholded area. And now you can see that we have 0.25 is that cut, and 0.25 in the x is this cut. So it actually corresponds to what we saw also here in this vector field. And other things we can do, we can also apply thresholds to other things. But yeah, here is just your imagination what you could play with these vectors. You could do some dot product with an axis, for example. Can also compute directions. So here we can compute the angle of the vector and say that this one, these and that angles should be segmented. So you can really play around with vector fields as you like, with mathematical sense, of course, and model-wise sense, but there are many degrees of freedom how you do the thresholding if you have a vector field, or even more degrees if you have a spectral image. And that finishes my part about the basic thresholding. And next part we're going to look into how to evaluate how we do the thresholding, and that is the next part of lecture 4.